There's a problem from 1859 that nobody has solved. If you solve it, you get $1 million. Cash. Sitting there, waiting. The problem is about prime numbers. You know, those numbers greater than 1 that only divide by themselves and 1. 2, 3, 5, 7, 11. Simple. And yet this problem has outlasted empires, world wars, and every single iPhone release. It's called the Riemann Hypothesis. And it's not just a math puzzle. It's a bridge between the chaotic world of primes and the perfect order of complex numbers. And if that bridge collapses, the internet gets a lot more interesting. But not in a good way. So, what's the big deal? Primes. They're the atoms of arithmetic. Every whole number is built by multiplying them together. 6 is 2 times 3, 30 is 2 times 3 times 5. They're fundamental. And they're annoying, because their distribution is a mess. Look at a number line. 2, 3, 5, 7. Then a gap. 11, 13. Another gap. 17, 19. Then nothing for a while. 23, 29. It feels random, like someone threw pepperoni on a pizza blindfolded. Some slices have 3, some have none. No pattern, no rhythm, just chaos. Mathematicians hate that. They want a rule, a formula. Something that says the next prime will be here. And for centuries, nobody had one. They just had a rough guess. The guess is called the Prime Number Theorem. It says, if you want to know how many primes are less than a given number, take that number and divide it by its natural logarithm. Roughly, it's like guessing how many pepperoni slices are on the pizza by weighing it. Pretty good. Not exact. The error is the problem. The formula gets close, but it wiggles. Sometimes over, sometimes under. That wiggle is the entire mystery of prime numbers. And in 1859, a German mathematician named Bernhard Riemann found a way to explain the wiggle. He didn't just weigh the pizza. He looked at the recipe. Riemann invented a function, the zeta function. It's an infinite sum. 1 over 1 to the power of s, plus 1 over 2 to the s, plus 1 over 3 the s, and so on. Boring. But here's the trick. That infinite sum is also equal to a product over all primes. 1 over 1 minus 2 to the minus s times 1 over 1 minus 3 to the minus s times 1 over 1 minus 5 to the minus s. Every prime gets a term. That's the Euler product. And it means his boring infinite sum secretly contains the entire DNA of prime numbers. Riemann then did something wild. He extended his function to complex numbers. Numbers with a real part and an imaginary part, like 2 plus 3i. Suddenly, the zeta function wasn't just a flat line, it was a landscape, with peaks, valleys, and zeros, places where the function equals 0. And those zeros, Riemann realized, control the prime wiggle. Their locations determine exactly how far off the prime number theorem is. Find the zeros and you tame the primes. So where are these zeros? Some are boring, negative even integers, -2, -4, -6. They're called trivial zeros. Ignore them. The interesting ones are in the critical strip, the region between 0 and 1 on the real axis. Riemann calculated a few. They all had a real part of exactly 1/2. And he made a guess. A hypothesis. All non-trivial zeros lie on the critical line, the vertical line where the real part is exactly 1/2. That's it. That's the Riemann hypothesis. One sentence. All zeros on the line. If it's true, the prime wiggle is as small as possible. The pepperoni is scattered, but not too scattered, but the pizza is perfectly balanced. If it's false, there's a 0 off the line. And that means the primes have hidden clumps. Secret structure. The pizza has a weird lump of pepperoni nobody expected. So is it true? We don't know. But we've checked. A lot. Computers have calculated trillions of zeros. Trillions. Every single one sits politely on the critical line. Not one rebel. Not one 0 with a real part of, say, 0.4999, all exactly 1/2. That sounds like proof, right? Wrong. Infinity is big. Trillions are nothing. You could check a Googleplex zeros and still miss the one weird 0 hiding somewhere beyond. It's like checking every pizza in New York and concluding no pizza in the universe has pineapple. You haven't been to my cousin's house. Math doesn't care about your trillion samples. It demands a logical proof, a chain of reasoning that shows no 0 can ever leave the line, and that proof has evaded everyone for 166 years. Why does it matter? Because primes are not just a playground for mathematicians. They run your online banking. RSA encryption, the thing that keeps online transactions secure, relies on the fact that factoring large numbers is hard. You take two huge primes, multiply them, and publish the result. Anyone can see the product. But to break the encryption, you need to find the original primes, and that's like trying to unbake a cake. If the Riemann hypothesis is false, it means primes have hidden patterns. Those patterns might suggest new ways to factor large numbers. Faster ways. That would be bad for RSA. But it's not an instant apocalypse. A disproof doesn't hand you a factoring algorithm. It just hints that one might exist. The real near-term threat to encryption is quantum computers if they become sufficiently powerful. They can factor large numbers efficiently using Shor's algorithm, and they don't care about the Riemann hypothesis at all. So the million-dollar problem is not a master key to the internet. It's more like a loose thread. Pull it, and something might unravel, or might not. The real stake is mathematical. A proof would be a revolution in number theory. It would connect two worlds that have been awkwardly dating for over a century. So who's tried? Everyone. Hardy proved in 1914 that infinitely many zeros are on the line. Great, but infinitely many could still leave room for infinitely many off it. Selberg proved in 1942 that a positive proportion are on the line. Better, but still not all. Obisco computed billions of zeros in the 1980s, all on the line. Gordon computed trillions more, still on the line. In 2018, a famous mathematician named Michael Atiyah claimed a proof. The math world got excited. Then the proof turned out to be, well, not a proof. He died a few months later. The problem survived him. Other amateurs send in proofs every year. They're usually full of errors. Some are clearly flawed. The Clay Mathematics Institute put the Riemann hypothesis on its list of 7 millennium problems in 2000. $1 million for a correct proof. $1 million for a correct disproof. Nobody has claimed it. The prize sits there, unspent, mocking us. What would a solution actually mean? A proof would confirm that primes are as well behaved as possible. The wiggle is minimal. The pepperoni is evenly distributed, statistically speaking. A disproof would be more interesting. It would mean there's a zero off the line. That zero would correspond to a hidden wave in the prime distribution, a new kind of pattern. It might open up entirely new areas of math. It might not break RSA, but it would shake number theory to its core. Either way, the person who solves it gets $1 million and a permanent spot in history books. Not bad for answering a question about a vertical line. And after 166 years, that line is still there, glowing in a complex plane. Trillions of zeros sitting on it like obedient birds on a wire. And somewhere out there, maybe, one zero is not. Or maybe not. The problem is a monument to human cleverness and human limitation. We can compute zeros until the universe dies. You'll never reach infinity. We need an idea, a new way of seeing. The Riemann hypothesis is a locked door. We've been knocking since 1859. The $1 million is still on the table. The pizza is still on the table. And the question mark floats above it all. Will it ever be solved? Maybe. Maybe by you. Stranger things have happened. Now, if you'll excuse me, I'm going to order pizza, half pepperoni, half nothing, perfectly balanced, almost.